If you thought probabilistic programming was cool, wait till you see SciML. What's SciML? Well, let's find out. Welcome to Doka.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. For the sake of discussion, let's simplify the differential equations problem-solving workflow into these three stages: input, function, and output. As long as you know two of the three stages, you can figure out the third stage. If you know the input and you know the function, then you can find a numerical solution for the output. That's just numerical computing for differential equations, which you can solve by using a package like differentialequations.jl. If you know the input and you know the output, then you can approximate the function by using an artificial neural network. That's just using machine learning as a universal function approximator, which you can solve by using a package like flux.jl. If you know the output and you know the function, then you can find the approximation to the probability distribution of the input using inference. That's just probabilistic programming, which you can solve by using a package like Turing.jl. But what if you only know the output? Is it possible to approximate both the function and the input if you only have the output? This is a common problem in science. You design an experiment and collect a bunch of time series data. But where do you go from there? How do you convert that output data into a function that explains your observations over time? And if you can't figure out that function, then how can you figure out the inputs? Where can you go to find tools to help solve this seemingly impossible problem? Welcome to SciML. It seems like one of the visions of SciML is to build tools to help scientists solve these seemingly impossible problems. SciML is short for Scientific Machine Learning. SciML is not a single Julia package. SciML is more like a one-stop shop for scientists who are seeking state-of-the-art tools when it comes to scientific computing. SciML is a convergence of many different disciplines, including differential equations, machine learning, and probabilistic programming. While each of these disciplines are great on their own, they're really impressive when they work together. SciML offers a glimpse into what the future holds for scientific computing. SciML was created by Chris Rackauckas, who is also the creator of the differentialequations.jl package and many other Julia packages. SciML has grown into a very large project with a lot of different contributors. In this video, I will provide a very small glimpse into the expanding SciML universe by going through a demonstration that will show the potential of using tools made available through the SciML ecosystem. This demonstration comes directly from the SciML documentation, and from this 2020 research paper authored by Raj Dandekar and others, titled Bayesian Neural Ordinary Differential Equations. The paper refers to something called the spiral ODE model. In the interest of time, I've prepared a Pluto notebook to show you what the spiral ODE model looks like. You can find this Pluto notebook in my GitHub repository. The spiral ODE model is a system of two ordinary differential equations, or ODEs. The system has two variables, u sub 1 and u sub 2. U sub 1 and u sub 2 are both cubed, so these equations are cubic ODEs. And the system has two parameters, alpha and beta. Conceptually, this system is similar to a sine wave and a cosine wave that decay over time. And as their amplitude gets smaller, the period gradually gets longer. As a result, the phase space looks like a spiral in the shape of a rounded square. When the value of the parameter alpha is small, the wave period is also small. And when the value of the parameter alpha is large, the wave period is also large. When the value of beta is negative, the spiral decays in a counterclockwise direction. And when the value of beta is positive, the spiral decays in a clockwise direction. So if you're given this system of cubic ODEs, it's relatively simple to solve by using the differential equations.jl package. But what happens if you're a scientist and you're recording observations from your experiment over some period of time, and your observations look something like these plots? You have a collection of time series data, so you know that your observations can be explained by some differential equation or system of differential equations. But you won't necessarily know what that equation or equations will be just by looking at your data. So if you don't know the equation or equations, then of course, you won't know the values of the parameters that are required for that equation or equations. So as a scientist, how can you start with your data and then work backwards to 1. Find an approximation of a function or a model that explains your observations, and 2. Find an approximation of the posterior probability distribution or the values of the input parameters to use with that model. Solving this problem is exactly what we're going to do in the SciML demonstration. The code for this demonstration is not intermediate level code. I consider it to be advanced level. Since I consider myself to be an intermediate level Julia coder, I have to confess that much of the code that I'm about to share with you is beyond my level of comprehension, especially when we get to the probabilistic programming section. As a result, I won't be able to explain everything. But I still think that it's valuable to go through this code, not only to demonstrate what's possible by using SciML, but also to keep pushing myself beyond my comfort zone. Let's start by creating a new Pluto notebook. Next, we need to load a bunch of packages. Just a warning, this may take a few minutes to load all of these packages, depending on your computer and your internet connection. Okay, now that we have all of our packages loaded, let's generate some data. This data is meant to simulate 40 observations over 1 unit of time. At this point, you don't know the differential equation or system of differential equations that can explain these observations over time. The code that we're using to generate our data is just standard code for the differential equations.jl package. Okay, so this matrix is meant to represent our observed data. Row 1 contains the observations for u sub 1, or variable number 1. And row 2 contains the observations for u sub 2, or variable number 2. Let's plot this data to see what it looks like. So these are the 40 observations for variable number 1. Now let's add the 40 observations for variable number 2. At this point, the data sort of looks like a sine wave and a cosine wave, but not really. Let's take a look at a phase space plot to gain further insights. So this is an interesting plot. At this point, it's not clear what's going on, other than the observations start at coordinate 2, 0, and then the observations move in a counterclockwise direction. We only have 40 observations over 1 unit of time, so that's not a lot of data. But given this limited set of observations, let's see how we can back into a model that can explain these observations. Now that we have our data, the next step is to build an artificial neural network using the flux.jl package combined with the diffeq flux.jl package. The result will be something called a neural ODE. This code will build a fully connected artificial neural network with 2 input nodes, 2 output nodes, and 50 hidden nodes. The network uses the tanh function as the activation function. By default, Flux will use 32-bit numbers, so you need to specify 64-bit numbers for higher precision. The result is a network with 252 parameters. The anonymous function used in this Flux chain is interesting. Using this anonymous function is informing the neural network to try cubing the variables in the function. According to the diffeq flux.jl documentation, by including this assumption in the model, this can reduce the required size and training time for the neural network. In this case, we just happen to know that our data resembles a cubic ODE. But for the data in your own experiments, you may not know what that equation looks like. So you'll either have to make an educated guess or leave this blank. I tried running this code without using this anonymous function, so I can confirm that this code still works. Now that we have the neural network defined, we need to define the ODE problem as a neural ODE problem using the diffeq flux.jl package. The neural ODE function is similar to the ODE problem function from the differential equations.jl package. But instead of using a standard ODE function as an argument, you use a neural network as your model. This line just assigns the default random number generator to the variable RNG. And this line just assigns the parameters from the neural ODE to the variable P. As you can see, this array has been initialized with 252 random values. So that does it for the neural network definition and the neural ODE problem definition. Next, let's define the loss function to use with our neural ODE. These functions will allow us to compare our data with the predictions made by the neural ODE, so we can try to minimize this loss value. ABS2 is a Julia base function that returns the squared absolute value. And that's it for the loss function. Next comes the challenging step. Using these definitions for the neural ODE and the loss function, we need to use probabilistic programming to infer the approximation of the posterior probability distribution regarding the values of the parameters for the neural ODE. This step gets pretty complicated, so I won't be able to explain most of this code. This is the probabilistic programming portion of the code. You can find the workflow for this step in the documentation for the advanced HMC.jl package, which is part of the Turing.jl ecosystem. HMC stands for Hamiltonian Monte Carlo. Finding the integrator may take a few minutes. The code in the SciML documentation draws 500 warm-up samples and 500 posterior samples. I tried running this code on my computer, so I can confirm that it does work, but it took over 30 minutes to run. So for this demonstration, I'm only going to draw 50 samples. The results won't be as good, but they should be good enough to get an idea of what's going on. If you run this code in the Julia REPL, you'll see the progress bar in real time. But Pluto doesn't display the REPL output in real time. Instead, Pluto records every change to the progress, so you can scroll through this output if you're interested in seeing how it changes over time. Okay, so we're essentially done. Now all we need to do is take a look at our results. Let's start by prepping our data for plotting. Each row is a parameter, and each column is a sample. So there are 252 parameters and 50 samples. Now that we have our plotting data, let's update our time series plot. A for loop is generating solutions of the neural ODE on samples of the neural network parameters, and checking the results of the predictions against the observed data. For some reason, plots are displayed in low resolution whenever there's a lot going on in the plot. But as we'll see shortly, when we save the plot to disk, this plot will be saved as a high-resolution file. So these lines represent the degree of uncertainty regarding the parameters for this model. We can also display the prediction that achieves the minimum value for the loss function. The first row is the best prediction for variable number 1, and the second row is the best prediction for variable number 2. This code will plot the best prediction for variable number 1. And this will add the best prediction for variable number 2. We can save this plot by using the savefig function from the plots.jl package. As you can see, it's a high-resolution image. Because we only drew 50 samples, the best predictions aren't great, but they do generally follow the shape of the observations. Drawing more samples will help improve the accuracy of the predictions, but the trade-off is that it takes more computing time to process those extra samples. The translucent lines represent the uncertainty of our predictions. So even if our best prediction doesn't fit the data exactly, the observations generally fall within the probability distributions. Now let's update the phase space plots. And let's add the best prediction that minimizes the value of the loss function. Let's save this plot as well. Similar to the time series plot, the best prediction here isn't great either, but the best prediction does generally follow the shape of the observations. Again, the translucent lines represent the uncertainty of our predictions. So even if our best prediction doesn't fit the data exactly, the observations generally fall within the probability distribution. What we did was we used probabilistic programming to infer the approximation of the posterior probability distribution of the parameters of the neural ODE, which is a machine learning model for a system of ordinary differential equations. And we did all of that by starting with just 40 observations. And then we worked backwards by combining differential equations, machine learning, and probabilistic programming. Needless to say, this is light years ahead of the coin toss experiments. We're living in a golden age of scientific computing. Never before in human history have scientists had access to so many tools to aid in the discovery process. Now, the code for this demonstration was state-of-the-art in the year 2020, so it's already been a few years. Currently, there's a lot of research going on in the field of scientific computing, so new tools and techniques are constantly being developed. It should be very exciting to hear about all of the discoveries that are made over the next several years. If you're interested in keeping up with the latest state-of-the-art developments, be sure to watch JuliaCon 2023 later this year, where Chris Rackauckas is scheduled to be one of the keynote speakers. Also, be on the lookout for SciMLCon 2023, which will take place during JuliaCon this year. As you can tell, there's a lot going on, so get involved And don't let this golden age of scientific computing pass you by. If you made it this far, congratulations! If you enjoyed this video, and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free early access to all of my new videos. Thanks for watching, and good luck on your Julia journey.